Welcome everyone. Today we are diving into one of the most influential breakthroughs in natural language processing, BERT, which stands for Bidirectional Encoder Representations from Transformers. It was developed by researchers at Google AI Language. This model was designed to pre-train deep bidirectional representations from unlabeled text by jointly conditioning on both left and right context in all layers. Before BERT, models like OpenAI GPT faced a unidirectionality constraint, meaning every token could only attend to previous tokens in the self-attention layers. While functional for generative text, this restriction is highly damaging for token-level tasks like question answering, where it is crucial to incorporate context from both directions simultaneously. BERT breaks this constraint by conditioning on left and right context jointly across all layers to prevent a word from seeing itself in a multi-layered context. BERT uses the masked language model trick by randomly hiding 15% of the input tokens. The model is forced to predict the original vocabulary ID using only the surrounding bidirectional context. Let's look at the competition. Unlike OpenAI's GPT's left-to-right transformer decoder or Elmo's shallow concatenation of independent left-to-right and right-to-left LSTMs, BERT uses a deeply joined bidirectional transformer encoder. This allows BERT to fuse context from both sides at every single layer. The BERT framework consists of two steps: pre-training and fine-tuning. First, we pre-train the model on massive amounts of unlabeled text, specifically 800 million words from books corpus and 2.5 billion words from English Wikipedia. To build a general understanding of language, then we initialize with these parameters and fine-tune all parameters end-to-end for specific downstream tasks like MNLI, NER, or Squad. How does BERT actually read? It utilizes word piece embeddings with a 30,000 token vocabulary. For any given token, the input representation is the sum of three embeddings: token, segment, and position embeddings. It also uses special tokens, CLOs, at the first token for aggregate sequence representation and SEP to separate sentence pairs. Masked language modeling in the first pre-training task, 15% of tokens are randomly selected for prediction. To mitigate the fact that masked token never appears during fine-tuning, BERT uses a mitigation rule. 80% of the time, the chosen token is replaced with mask, 10% with a random one, and 10% stays unchanged. This forces the model to keep a distributional contextual representation of every token. The second engine is next sentence prediction, which is critical for question answering and natural language inference. BERT is trained to predict if sentence B actually follows sentence A. 50% of the time it is the real next sentence, and 50% it is a random sentence. Remarkably, the model achieves around 97 to 98% accuracy on the task during pre-training. One of the bird's greatest strengths is its unified architecture. Whether you are working on sentence pair like MNLI, question passage pairs like squad, single text like SST2, or sequence tagging like NER, you use the same pre-trained engine and just add one task specific output layer. Does it work? Absolutely. BERT achieved state-of-the-art results on 11 natural language processing tasks. It pushed the GLUE score to 80.5%, 7.7% absolute improvement, and outperformed human experts on common sense inference benchmarks like SWAG with an accuracy of 86.3%. Scale matters. We see a significant jump in performance between BERT-based 110 million parameters and BERT-Large 340 million parameters. Critically scaling to extreme model sizes leads to massive strict accuracy improvements even on very small scale tasks like MRBC, which has only 3600 level examples. By stripping BERT down, we see that every piece is non-negotiable. Removing next sentence prediction causes performance to drop significantly on QNLI and MNLI. Moving to a left to right LTR architecture results in devastating drop from squad and MRPC, proving that token level hidden states fail without right side context. While fine tuning in the standard, BERT is also highly effective as a feature based tool for tasks that don't fit perfectly into a transformer encoder. In the CoNNL 2003 NER test, extracting and concatenating the top four hidden layers, yielding a 96.1 F1 score, which is nearly identical to the full fine-tuned model while saving massive computational costs. In conclusion, BERT has established a new foundation for NLP based on three pillars: paramount bidirectionality, universal pre-trained representations, and unprecedented transferability. By allowing low resource tasks to benefit from massive retraining, BERT has successfully conquered a broad set of language understanding benchmarks. Thanks for watching. Make sure to check the original paper for the full technical details on this bidirectional breakthrough.